Hello and welcome back, everybody. Today in calculus, we're going to, conclude our talk on the sequence and series, and also the Taylor and Maclaurin in chapter 11 in this case. So this is basically just kind of like, conclusion for all the stuff that we've been doing so far. So in a way, make it a fun topic if you want, okay? So underneath right here, you should be able to see that we actually have a list of all the series that is actually worth memorizing. These are the power series that are worth memorizing, because with these power series, the 7 over here, you can pretty much build anything that you want. On the side, you can see that the equation is there, and then in the middle, that's going to be the power series that goes along with it. And on the right-hand side, you have the radius of convergence, or the interval of convergence then, okay? That is basically just all the stuff that we've covered all the way up until this point. Now, this video is going to focus on 3 of these that actually look very, very similar, and I want to say that there is a relationship between them. The 3 that I'm looking at actually will be e to the x, sine of x, and also cosine of x, because if you write them out individually, you'll notice that they look almost about the same thing. In fact, I want to say that they might be able to overlap. So let's go ahead and go down here and see what I'm talking about right here. So here you can see e to the x, cosine of x, and sine of x, and then their respective power series. Notice how cosine is going to be all the even power terms, and then sine would be all the odd power terms, whereas e to the x would be then the combination of the two, because it consists of all the odds and also the even. Now the question is, okay, well, is there a relationship between these 3 power series? And the answer is yes. The question is, well, then also, how do you relate them? Because the problem is that cosine and sine, it's not quite like e to the x, because they alternate between each terms, whereas e to the x is always going to be positive. So that means that I need to do a little bit of thinking about like how this actually going to work out. So here, let's go ahead and think about this then. For cosine, right, you'll notice that you're going to go from positive to negative and positive to negative. So that means for e to the x, I need to somehow make this term right here negative. And then afterwards, if I were to write out x to the 6, let me go ahead and write that in, x to the 6 over here. I'm going to have to somehow make that term negative as well. So that means that there should be a -1 right here and a -1 right here. Then similarly for sine, right, you'll notice that x to the 3rd is negative, and then x to the 7th is negative. So that means I need to somehow make this guy over here negative, and then I also have to somehow make the next term, if I were to write it out, which I will, x to the 7th divided by 7 factorial, that somehow has to be -2, whereas everything else is going to be positive and positive and so on and so on and so on and so on. So when you write it out that way, then hopefully you can kind of see like what kind of pattern is it that I'm trying to generate here. So let me go ahead and maybe write those in a different color, just so that it's a little bit easier to see. So these first 2 terms, I need them to be positive. Then the 5th and the 6th term, I need them to be positive, but whereas the 3rd and the 4th has to be negative, and then the 7th and the 8th term would also have to be negative. So then the question is, okay, well, how do you make that alternation then? The one thing that, if you remember back in Algebra 2, that is going to be similar to this is the following. If we have I, right, that is supposed to be equal to square root of -1. If we have I squared, then that's going to give us -1. And then if we have I cubed, that's going to be equal to -I. And then if we have I to the 4th, that's going to be equal to 1. So right there, if I can somehow implement this imaginary number in there, then I think that will do the trick, because this is what's going to allow me to go from 2 positive to 2 negative to 2 positive to 2 negative, and so on and so on and so on. So let's go ahead and do that then. For my power series for e to the I, what I'm going to do is I am going to go ahead and replace all the x's with ix. Okay, I'm going to replace all the x's with ix and see what's going to happen. So let me go ahead and pull down some of these guys right here, just so that I can make a little bit more room, if it's okay. Okay, so let me go ahead and put this over here and erase some of this and some of this and so forth. Okay, all right, so there we go. All right, so now let's go ahead and write that in then. So x to the 7th, oops, Sorry, a little bit of small technical difficulty. So x to the 7th and then 7 factorial. All right, so here we go. Replacing all the x with I to the x, okay? I times x. And keep in mind, I is supposed to be equal to square root of -1. Now, if I were to put that in there, then here's what I get then. The first term is going to be just 1. The second term is going to be ix. And then the third term is supposed to be I squared, right? It's supposed to be ix quantity squared divided by 2 factorial. Then the next one is going to be ix to the third divided by 3 factorial. And then plus ix to the fourth. And then we have 4 factorial. And so on and so on and so on. Okay, so that's what it looks like if we were just to do a replacement. So after this, what happens next is we're going to have to simplify to see what happens then. Okay, so we'll go ahead and do a few terms and hopefully you can see what's happening then. The first term, it is still going to be 1. The second term is just going to be ix. The third term right here, I squared, well, that's where it's going to give us the negative. So, hey, now it's starting to work out because then we have that negative x squared divided by 2 factorial that we want. Then the term afterwards, we have I cubed, which gives us negative I. So there's going to be an I in front, and then we have x to the third, and then divide by 3 factorial. I to the fourth, that is equal to +1. So now we alternate back into the positive. And then now for the fifth, it's going to be I times x to the fifth divided by 5 factorial. And then we have minus I to the, oh, sorry, there's no I. So that's just going to be x to the 6th divided by 6 factorial because I to the 6th is -1. And just to do one more term, I to the 7th, that becomes negative I multiplied by x to the 7th divided by 7 factorial. Okay, so there you go. Now let's go ahead and take a look then. For cosine, right, we're looking at the even terms. So here's my even term. That right there checks out with this. This right here, that checks out with this, so that's good. And then we have, let's see, x to the fourth, and then you have 4 factorial, and then that checks out with that. And then we have negative x to the 6th, so that checks out with that. So yeah, it looks like it does match up with the cosine of x. Now, whereas for the sine of x, now let's go ahead and compare those then. This right here, in comparison to down there, it looks like I do have the first term, but I have an extra I. And then for this, for x to the third divided by 3 factorial, then that looks like the same thing, except also I have an I. Then for x to the fifth, I have the same thing over here with an extra I, and so on and so on and so on. So what I'm noticing is that, yeah, it looks like it's going to be cosine of x plus I times sine of x. I'll repeat it one more time. Cosine of x plus I times sine of x, because all the sine terms, right, there's an extra I that's in front. So what ends up happening is what I have, which is e to the ix, is supposed to be equal to cosine of x plus I multiplied by sine of x. And right there, there's your relationship between all of them. So here, if you remember, on the right-hand side, that actually looks like the form for a complex imaginary, and that's no coincidence whatsoever. This is what we call Euler's formula also. There are actually more than one of them, and this is probably the more famous one. Now, to put a conclusion to this, because this is probably the most interesting part, is why don't we go ahead and let x equal to pi? If you do so, then we have e to the I times pi is equal to, on the right-hand side, we have cosine of pi, which is going to be -1, and then plus I times sine of pi, which is going to be 0. So cleaning that up, you get something very, very unique, which says e to the I pi is equal to -1. And this right here, even though it doesn't really do form too much for us, for mathematicians and so such, it's kind of a beautiful thing, I suppose, because this is where you have a relationship between 4 of the most distinct numbers in math. All together in one single equation. And if you want, I guess you can put the 1 onto the other side because that's a little bit more common. So e to the I pi plus 1 is actually equal to 0. So this is, for what I learned a while back, my professor called it kind of like a math nerd nerve orgasm in a sense, because this is like, the thing that kind of like makes all the math people just kind of like giddy and stuff. But anyhow, thank you so much for watching, and that should pretty much be it then. All right, I will see you next time. Goodbye.